The speaker, Andrew Chael, is from Princeton University. He is an expert in astrophysics and astronomy, and is going to talk on imaging black holes for the next hour. Please join me to welcome speaker.
Great. And this mysterious dark spot is the best evidence we have for a black hole of about 4 million solar masses. Zooming even further, until about 5 years ago, this is the best image we had of that black hole, of the super hot plasma surrounding the black hole. And you can see that there was basically no information. It was completely blurred out. And so the question was, if we zoom in even further and actually are able to look at this thing on scales of the event horizon, what would we see? 1,000 times further away from our own galaxy, the galaxy M87 launches this spectacular extragalactic jet, as you see in this image from the Hubble Space Telescope, this extreme jet of matter moving at nearly the speed of light, moving away from the center of this galaxy. And over the past 50 years, people have tracked this jet in radio light using higher and higher resolution observations with very long baseline interferometry, until, again, just about 5 years ago, this is the best image we had, where you can see very close to the center, the launching point of this jet, here on the scale of less than a light year versus thousands and thousands of light years here. But we didn't know exactly what was here hiding at the core. We think this was also a supermassive black hole, about 1,000 times bigger than the black hole in the center of our own galaxy. But again, when I entered the field about 5 years ago, this was the best image we had, and we couldn't resolve the detail on these scales. So people for a while had thought about what a black hole would look like if you could look at it on scales of the event horizon. And you can sort of make a schematic argument for what the image would look like just by considering that this black hole is lensing the light near it, and some of the light, if you track light backward from the observer, will end up on the black hole itself, while some of it will escape to infinity. And this manifests in the image. This is a simple model as this large shadow feature, which you can calculate analytically the size of it. It's about 5 times the Schwarzschild radius. When you put that really far away, this turns out to be the size of 40 microarcseconds for the black hole in M87, and about 50 microarcseconds for the black hole in our own galaxy, Sagittarius star. And this microarcsecond is a really strange unit, but basically it means it's less than 10 to the minus 8 degrees. It's extremely, extremely small. And this sort of general structure has also held up in more modern simulations. So we had a good idea of what we might see if we could zoom in with this extreme resolution. Unfortunately, this is incredibly small, and it takes a lot of work to actually resolve this. Just to give you a sense of how small this is 1 pixel in the Hubble Space Telescope, and zooming in to many, many, many times smaller than that single pixel, you can see how big our image of the black hole is. Now, the image of the black hole is so small that even with a telescope the size of the Earth, we can only barely resolve it. So the resolution of a telescope is equal to its wavelength over the diameter. And if you consider that we had a telescope the size of the Earth, we've used the wavelength of light that we need to observe at for these black holes, which is 1.3 millimeters. This is where they're brightest. You can see that we only have a resolution of about 20 microarcseconds, which is just barely enough to start to resolve this shadow or donut-shaped feature around the black hole. We think from simulations that we have all this fine structure, but with even the telescope the size of the Earth, we only can barely peek it out. Now, of course, we can't really build a telescope the entire size of the Earth. I don't think any funding agency would approve that, but we do have the ability to link telescopes from around the world in this technique called very long baseline interferometry, where basically what we do is we take signals from each telescope and synthesize them together in providing us the resolution effectively of a telescope, the size of the maximum separation between the telescopes. And this project, the Event Horizon Telescope, which has been going now for more than 10 years, is an international collaboration to do just that, operating at the highest frequencies we've ever done this technique. And it connects telescopes all over the world, basically giving us the effective resolution of an Earth-sized telescope. And of course, with this telescope, the Event Horizon Telescope, we've been able to actually zoom into the final and take the final zoom in and make images of the black hole, both in M87, where we have a black hole of billions of solar masses, thousands, millions of light years away, and in our own galaxy, Sagittarius star, where we have a black hole about 1,000 times less massive, but 1,000 times closer. And so the EHT is really, I think, a triumph of international collaboration. It's only made possible by the fact that we have hundreds of members from over 60 countries and 5 continents, or 20 countries and 5 continents, really spanning the globe and working together to make this image possible. And I think that given that collaboration is the theme of this workshop, this is a really natural talk. Okay. Yeah, the EHT is really a collection of antennas, lots of software to extract the data out of those antennas, which I'll talk about a little bit next, and international teamwork to produce a computational telescope and make these images black holes. So in this talk, I'll talk a little bit about sort of the overall summary of how we made these first images of the black hole in M87, since that was the paper that this award was given to. And then I'll talk a little bit about what we've learned from these EHT images, a little highlights of the science that we've gotten to know over the last few years. And then I'll talk a little bit, if I have time, about next steps and the capabilities of the EHT and black hole imaging in general, both sort of on the hardware side and on the software side, what we're doing now to sort of extend the techniques we developed to produce the first black hole images. Okay, so first, how do we obtain these black hole images? How do we turn this set of telescopes into an actual image? So the basic technique that we use is called very long baseline interferometry. The idea is that you have 2 telescopes widely separated on the Earth, and each baseline or separation between these telescopes, if you cross-correlate the electric fields that you record at each telescope, provides one Fourier component of the image. So this breakdown of the image into sine waves, we can sample one component of that by looking at the signals correlated between these 2 telescopes. And so that gives us only a very small piece of the image, of course, and we only have so many baselines. But we can rely on the fact that the Earth is rotating to sort of fill in this plane of complex frequencies in the Fourier transform, because as the Earth rotates, the separation between these telescopes, as seen from the source, changes in projection. We start to fill in measurements of the Fourier transform of the image, but even so, after a full rotation of the Earth, because we only have a finite number of telescopes around the Earth, we only have a small number of measurements in this Fourier plane. Therefore, we don't know the full picture of what the image looks like. We only have a small inkling of what the actual image looks like. So the EHT is this collection of 9 telescopes at 7 distinct geographic sites, spanning the world from the South Pole to Greenland and Hawaii to France. And in 2017, we took our first observations, and here's some pictures of people at the various telescopes in these observations. This is still a very hands-on process. Many astronomical observatories are now operated fully remotely, but because we're doing very specialized science and using very specialized equipment, people still have to go to these telescopes and do these observations by hand. Unfortunately, I'm not really qualified to do that, so I just sat in a room in Boston and watched on Slack, but still tried to contribute some emotional support. So once we have these data that we record at the telescopes, the data that we record measures in petabytes, because what we're recording is actually the full electric field, quantized to only a few bits, but the time series electric field that we record at each telescope over the course of several nights. And then we need to reduce this data down to an image which contains only a few kilobytes of information. And so this data reduction path is huge, and I'm only going to talk about sort of the last phase where we turn data that's already been reduced by orders of magnitude from the calibrated data into the image. But the sort of whole process of correlating and then calibrating is itself an incredibly important part of the EHT that required a lot of technical development, a lot of new software and techniques to take these data, to correlate them, and then to get the best quality calibrated data that we could use in the imaging process that I'll talk about. Okay, so the first thing is, after we take the data and we correlate it and we calibrate it, again, skipping over an enormous amount of work, we can just look at the raw data, and we can look at it in this way. We have on the x-axis the baseline separation. You can think of this as increasing spatial frequencies. As you go to higher and higher frequencies, you're looking at finer and finer structure in the image. And then we have the amplitude of the Fourier transform collapsed. It's a 2D Fourier transform. We're collapsing it to one axis here, just looking at the radius in the image plane. And you can see this characteristic bouncing structure in both of our black hole sources, M87 and Sagittaire star. This is already indication that in both sources we're seeing what could be a ring. Because if you think about what the Fourier transform of a ring is, it is actually a Bessel function, and that has this characteristic bouncing. And so this is already a hint, but there are other structures that could have bouncing in their Fourier transform. Things like a filled-in diff, for example, would have a different degree of this characteristic null pattern. And so we need to then take the next step and start to apply the imaging process to turn these data into an image in the image plane that we can understand. Okay, so this is a really hard process, and it's been developed over many years for many different telescopes, not just the EHT. In the past, operating at lower frequencies. And it's challenging for several reasons. So the first is that our data are sparse, like I talked about earlier. We only have a few measurements in this Fourier plane. We only have a few components of the Fourier transform of the image. And so we don't know what's going on outside of these measurement points. So we need to make some assumptions to sort of fill in the missing data in order to make an image. Basically, this is an ill-posed problem. The inverse Fourier transform from our set of sparse measurements is highly unconstrained, and so we have to make assumptions to fill in gaps. The way this has traditionally been done in interferometry over the last 50 years is through this deconvolution process. So you can think about it in the image plane. What we have is basically a true image, which is then involved with this very nasty point spread function. So basically, this is the Fourier transform of the sampling pattern itself, where we have only these few small points. We just take a Fourier transform of this map of ones and zeros. You get this essentially point spread function, and you would get this incredibly messed up, dirty image. And so the traditional approach to making images in radio astronomy has been to sort of take this dirty image and deconvolve it to essentially try to subtract out all this messy, dirty beam structure from this image to get something that looks much more like the source image. And so the traditional algorithm that has been used in this field to do this is called CLEAN, and it's been used for over 50 years, very successfully for the most part, for many different arrays. So the way this typically goes is you work in the image plane, you take the inverse Fourier transform of your data to get this dirty, fuzzy, messed up image, and then you do this iterative loop of trying to subtract off the point spread function to make a collection of point sources, which you think are converging to this the actual truth image. And you do this loop, and then at the end of the day, you have a collection of point sources, which you then blur out to make an image. So again, this technique has been very successful for the most part, but for the EHT, it posed a lot of difficulties, particularly in this first step of the inverse Fourier transform. This is because we have a second problem with the EHT for imaging, which is much more challenging than for other radio astronomy observations. Basically, our data are highly corrupted. And they're corrupted by the fact that we're operating at very high radio frequencies, and the Earth's atmosphere is not very cooperative at these frequencies. So if we think about the signals coming to our telescope, we have two different polarizations. We have, in the Earth's atmosphere, a lot of water vapor. And at these high frequencies, this water vapor scrambles the phases. Basically, it scrambles the arrival times of these two waves from the source, and so that we don't essentially receive any phase information from the source that we can use in our Fourier transform. We also have amplitude gains from miscalibration. Basically, we don't have a really accurate way of measuring how intense these signals are. We can have huge errors in the amplitude. And then we also have mixing of polarizations in the electrons. I won't really talk about, but it's also very interesting. Okay, so this lack of phase information, and by the fact that we have this scrambling in the atmosphere, is incredibly important. Because if you think about taking this image and removing all of the phase information, basically we can no longer do an inverse Fourier transform to get anything that looks anything like a dirty image. We basically get something that's completely messed up. The phase contains most of the information in the image, and if we just zero it out everywhere, we have no starting point for the traditional clean algorithm. We have nothing real in this image to try to subtract away this point spread function structure from. fortunately, while we don't have phase information on individual baselines, we do have this set of measurements that we can make that are robust to this corruption, which are called closure quantities. I won't get into too much detail on these, but basically these are clever ways of combining information around triangles or quadrangles of telescopes, which cancel out all these um, corruption or systematic factors in our data. Basically, the fact that we have phases at different stations and gains at different stations, we can cancel out by taking these different combinations of our data. This is basically a consequence of the fact that our corrupting factors are occurring at each station, but our measurements are occurring at between pairs of stations. So essentially, we have more measurements than we have corrupting factors, and so we're able to take these combinations to account a little bit for what we might observe in truth if we could peer through the atmosphere. Okay. So when I entered the field, we were basically just starting to explore a new approach of imaging algorithms, which today I think is quite basic and primitive, but at the time was, I think, a significant advance brought forward from what we were doing with clean. So essentially, the idea is instead of trying to deconvolve or subtract out all this messy structure in the image, what if we instead try to just do a forward model and take and solve for the image directly, sort of just by fitting a huge array of pixels to the data. And of course, we can do this just by making a forward model of our instrument, trying to capture all the systematics that we know about, and then creating a log likelihood between our proposed image and the data that we measure, given our best forward model of the instrument, to try to produce some image that maximizes the likelihood or minimizes the negative. And one of the nice features of this approach is that we can be very flexible in the types of data that we use. So we don't have to use the individual measurements between telescopes. We can use these robust closure quantities, which cancel out all the systematics. Basically, we can use less data, but we can use data that we trust more, that is invariant to all these corrupting effects of the atmosphere and the miscalibration that we have. This is one of my first projects in the field. Basically, we showed that this is actually, both of these are using the invariant phases, but if we just consider these closure amplitudes, basically we were able to show that while using a sort of straightforward approach where we use different amplitudes on different sites, as we increase the calibration error, we lose the ability to reconstruct an image. This is here the truth image, and here is our reconstructions using the telescope, a simulated telescope. If we include this sort of additional method and include all these errors, we lose the ability to reconstruct things as we go to higher and higher errors. But by using these robust closure quantities directly in the imaging, we're able to actually get good images at any level of gain calibration error. Again, just as a consequence of the fact that we're sacrificing some information in using these robust quantities, and the optimization is much harder, but we are using things that are robust and invariant calibration. Now, of course, just trying to maximize the likelihood of this image in this forward model isn't going to give us a unique solution because we only have a limited number of data, and there's an infinite number of images that could potentially fit our measurements. You can sort of see this here. These images all have the same likelihood, a very high likelihood when compared to the data extracted from the truth image on the EHT in 2017. But some images, of course, we think are less likely a priori than others, and so we can just apply a prior here and do sort of a quasi-Bayesian imaging where we combine our log likelihood and prior to get our best guess of what the best reconstruction should be under both our data and our prior assumptions of what image structures are reasonable. Now, well, nowadays we actually do a full sort of rigorous Bayesian imaging in many different methods where we actually fully try to explore this posterior space. In the original EHT papers, we actually sort of simplified this into what we call the regularized maximum likelihood approach, where we're just trying to find a single best fit image under our log likelihood and sort of a set of flexible regularizers, which don't have to be sort of formal prior probabilities. And we explored many different combinations and choices for these sets, which impose different penalties on different features in the image. For example, favoring things like sparsity or smoothness. So what we were able to do is to sort of create this imaging framework where we have log likelihoods that are invariant to various corrupting factors. We have regularizers which favor different things in the image. So for example, we can explore regularizers that favor sparsity, images that are mostly empty space, or smoothness that favors images that are very slowly over small scales. There's sort of the classic maximum entropy method that we also explored. And we are able to sort of vary the hyperparameters for these different regularizers and explore how the imaging changes under different assumptions. And it's really by exploring this full space of hyperparameters and trying to understand how our images vary that we're able to get the best confidence about what features in the image are robust and what features are not. So yeah, as part of my PhD, I assembled a software package that does this, the EHT Imaging Software Library, which is a Python toolkit, and it's been used in basically every EHT result since the initial ones, and I think it's also very flexible and useful for imaging analysis and radio astronomy beyond the EHT. So if anyone here is interested in that, I'm happy to talk afterward. But it's basically a really flexible way of trying to take this framework of log likelihoods with different data products and regularizers that favor different or penalize different image features and combining them together to get the best quality. And it works beyond just the EHT images of black holes. So here's an example of a famous image of a protoplanetary disk from the ALMA telescope, where we have the original clean image has these very clear calibration factors, these dark patches that we don't think are real. With EHT imaging, we were able to smooth that out and get a higher quality image. And then if I have time later on, I'll talk about how we are able to actually combine now data from multiple frequencies and get an even higher quality image. Okay, that's just sort of a background on some of the new imaging techniques we developed now more than 5 years ago for the Event Horizon Telescope. But actually, the paper that I'm talking about mostly today, or the paper that won the award, is basically answering a different question, which is how do we verify what reconstructing is real? So we have many different ways that we can do this reconstruction process, that we can turn our data into an image of a black hole. But because all these different methods have different choices, and because all of them are trying to answer an ill-posed problem, where we are having to make some assumptions in the structure of our algorithm or in the regularizers or hyperparameters that we use, there, again, are an infinite number of possible images. We have no unique solution, and so we need to try to compare methods and try to investigate our method very rigorously in order to build some sense of confidence that what we're actually reconstructing is real features in the data, rather than something that's imposed by our imaging choices. And so this was the paper that sort of did this work, where we took all of our different methods and tried to rigorously cross-compare them and apply them to the first data set of black holes from the EHT and produce the sort of best guess, most conservative image of the structure that we really knew was real in around the black hole in 87. And I got to be one of the paper coordinators of this paper, which was a really great experience. These are the other 4 coordinators: Michael Johnson, Kazuo Akiyama, Katie Bowman, and Jose Gomez. And I do want to stress, though, that while we were the coordinators, this paper represents many, many contributions from people across the world and across the EHT collaboration. It's really one of the most collaborative things I've gotten to work on so far in my career, and it's a real pleasure. Okay, so again, so again, the key point of our paper was that we can't really rely on one single reconstruction method to produce an image of a black hole, because each method individually makes different assumptions that could bias the results, or could create structure in the image which isn't actually reflective of the underlying truth image. And so what we did was to test and compare many different reconstruction methods in order to arrive at the most reliable image, and to sort of account for all the biases and systematics that any one individual method could impose. We compared these both against each other themselves with synthetic data tests, and against each other in sort of these cross comparisons. And so we use an ensemble of clean-based imaging methods, or the standard method, which has the difficulties of having a really hard time working on EHT data with its phase uncertainties. These regularized maximum likelihood methods, which I talked about a little bit, that we developed, and then a new extension of Bayesian and CNC posterior exploration, where we sort of take the next step and do a full exploration of an image posterior with in this framework. Okay, so to do this cross comparison, we went through multiple stages. Again, trying to be as rigorous and careful as we could to validate at each step that our different imaging methods were producing consistent results and that we understood what their systematics were. The first stage that we did was a blind imaging stage, where we basically had different teams applying different imaging methods to the data that we sequestered from each other and had work in isolation so that we couldn't cross-compare notes and we couldn't, try to see what other people were getting and use what they were getting to bias how we approached the problem. And so we took the data release and we, again, separated into these 4 teams using different methods. And each team worked independently, I think for over some number of months. And we, at the end of the day, were able to produce these images, which were all very consistent with each other, at least in the sense that they have this prominent ring feature out of around the same size. We also built a sort of automated blind cross-comparison framework that would allow these to be compared without any human actually looking at them. And so, again, you can see that these images all have a very common feature of this ring. So we already at the end of this blind imaging stage were pretty confident this ring was a real prominent feature in the image. But they also look quite different in other ways. They have different extended features. The detailed structure of brightness around the ring is different. This is just a consequence of the fact that this is, again, an ill-posed problem, and there are different ways of approaching it. And we, different teams made different choices. And so we already start to get a sense of what features in the image are robust and which are not by looking at this initial set of images. The next thing we did after this blind imaging stage was to do a set of tests on methods with synthetic data. So we basically took each of our imaging methods and made sure that they could pass a wide variety of synthetic data tests, where we took different source morphologies and ran and created synthetic data from them using the best model we had of our telescope, basically to make sure that each method that we wanted to use in the final paper could distinguish between these different source morphologies. So could we distinguish between something that's like a double source or a point source or a filled-in disk versus something that's more of like a ring, which is what we think we were seeing in M87. And to various degrees, all of the different imaging methods that we use pass these imaging tests. And then basically what we did is we took these different imaging methods, which again have many different choices of parameters in them, and we subjected them to these surveys of trying to vary the hyperparameters that control the different algorithmic choices in the reconstruction, and testing how each hyperparameter combination responds to the synthetic data test. So we tested over 30,000 hyperparameter sets for each imaging method, and then we explored which ones apply best to all synthetic data tests. So which ones could work well not just on a ring-like image, but on every single image in our set, and distinguish between things like disks, double sources, crescents, and rings. And we applied only those sets of hyperparameters to the real data in producing images in the set. Okay. So then at the end of the day, we had each method had explored both synthetic data tests, had explored these different hyperparameter combinations. And then at the end of the day, the last comparison that we did was to compare different methods. So we have here in the final paper results from 2 regularized maximum likelihood methods, Smiley and EHT imaging, and 1 traditional clean-based method, diffmap. And you can see again, these are the final results after doing all these tests and making sure that we could reliably distinguish between non-ring and ring morphologies with synthetic data, and that we knew how our different hyperparameters were performing with these surveys. We saw this array of images covering 4 different days of observations, 4 different data sets, and 3 different methods. And again, you can see that each of these methods is producing a slightly different image, so they all have this prominent ring-like feature of the same size. And so again, to hone in only on the most conservative, most reliable information in these different methods, the structure that's common across all of them, we essentially did a very simple average of blurring the final method's images from each method to an equivalent resolution, and then averaging them together to really only focus in on the final, most concrete, robust results that was common to all methods and all approaches. So that was what we did now 5 years ago to get the first image. Since then, we've gone back to the source and we've looked multiple times at the black hole in M87, and we've shown, for example, that a year later, after the 2017 observations in 2018, that basically we see the same overall image structure, though there is some interesting variability as this brightness shifts around the black hole because things are moving very dynamically between these two. This was also observation performed with a more complete array, including the Greenland telescope, which made the image recovery process easier. Um, and again, it has a very consistent diameter, but a different brightness. It's very consistent with what we see in theoretical models. And then, of course, I'm not going to talk about too much about our image of the black hole in a galactic center, Sagittarius star. But this was, in many cases, I think it is actually a much more challenging problem, much more difficult problem than imaging M87 due to the rapid sub-hour variability that Sagittarius star experiences. So basically, our galactic center black hole is 1,000 times smaller than M87, so it moves 1,000 times more quickly, or stuff around it moves 1,000 times more quickly. And essentially, this produces a situation where we have structure around the black hole which is moving underneath our camera exposure, is the way to think about it. It's the difference between taking a picture of someone sitting still and a dog running really quickly. And this provided a lot of challenges for our imaging team. We went through a very similar process of careful validation, blind imaging, parameter exploration, and only focusing in on features common between different independent reconstruction methods. And at the end of the day, we recovered this image of Sagittarius star. And soon, hopefully, we'll be able to share some information about what Sagittarius star looks like in years after this to gain more confidence that this is a reliable structure. Okay, so that is just a brief overview of sort of the process of how we produce black hole images. Now I'm just going to provide a few highlights of what we actually learned from these images physically. Again, this is only a few highlights of a really large literature that has developed over the last 5 years about what you can learn from black hole images. But these are some of the things that I think are the most interesting. Very biased. But yeah, the first thing is really just trying to focus in on, again, what is consistent in the ring properties of M87. We recovered a very consistent diameter, again, between methods um, um, and across the different observing days. But the position angle seems to change, hence that we're seeing this intrinsic variability of plasma swirling around the black hole. This changes it even more when we consider not just a week of observations in the first set, but also multiple years later. And basically, this diameter is a really strong hint that we're seeing some sort of static persistent feature of space-time that's producing this consistent size, whereas the evolving position angle is giving us hints to the plasma dynamics or astrophysics around the black hole. So one of the first things we did was use this diameter to sort of try to make a mass measurement of the black hole, because the size of the black hole image is proportional to how massive it is. And the way that we did this was to first try to really hone in on a very precise diameter measurement by using geometric modeling. So instead of modeling a sort of flexible array of image pixels, to really try to focus in on a ring-like model and measure its diameter using MCMC exploration with Dynasty. And then accounting for all the different astrophysical calibration effects that could sort of disturb the simple relativistic relationship between mass and diameter, we were able to, with 3 different pipelines, use our diameter measurement in order to establish a black hole mass measurement, which agreed with basically the upper range of black hole mass measurements that have been made previously, looking at the influence of the black hole on the large-scale structure in the galaxy. So in particular, it agreed with the measurements that were made from stellar dynamics of the black hole mass in 2011 versus gas dynamical measurements of the mass in 2013 produced a mass that was a factor of 2 smaller. We can sort of turn this around, and again, with Sagittarius star, we have a very precise mass measurement because we're able to actually observe things orbiting it. So if we assume that we know the black hole mass, we can then ask how consistent is our imaging with the prediction from general relativity? How consistent is the size of our image with general relativity's prediction, given all our astrophysical uncertainties which you have to account for? And we find for both sources that as long as in M87 we assume the previous measurement of stellar dynamical mass, that we are consistent with the prediction from general relativity in this sort of extreme supermassive case, which has never been probed before directly with imaging. So that's just what we learn about sort of the mass of the black hole and some things about general relativity. Um, I mostly focus on what we learn about astrophysics, what we learn about the gas and plasma surrounding the black hole, where we have essentially around the event horizon of M87 a thick accretion disk of plasma that's tens of billions of degrees Kelvin. It's threaded by strong and turbulent magnetic fields and launches this powerful relativistic jet. And so we can also try to learn things about what exactly this plasma environment is and how the black hole eats matter and ejects energy. And the way that we do that is by comparing our images to images obtained of simulations from general relativistic magnetohydrodynamics. So we run these 3D simulations of plasma and magnetic field evolving in the curved background of a black hole. And then we produce images from them using general relativistic ray tracing, accounting for the reflection of photon trajectories through this strongly curved spacetime in order to produce movies of the swirling plasma around black holes like this one. And then we can compare large libraries of these images to our actual observations in order to try to match which astrophysical parameters in the simulations are most consistent with our images. So we've built these simulation libraries. I think the first one had 60,000 images. Nowadays they have even more, covering a range of parameters in these different supercomputer simulations, including spin, temperature, magnetic field geometry, etc. So actually it turned out that in the first results, we had a bit of a problem in that our simulations matched the images almost too well. And this was not anything that we were imposing, right? We didn't actually use these simulations at all to inform our imaging. The imaging is entirely independent from the simulation. But if we just take the EHT image and we take a simulated image and run it through the same imaging pipeline, again, the imaging pipeline does not depend on the simulation itself, we just run the data through the pipeline, we get something that looks very similar to the EHT image. And the initial images that we considered were consistent with almost all of our simulations after accounting for free parameters that we can adjust, like the overall size. And so that was exciting in that it says that our general picture of what's going on around these black holes in the simulations is probably pretty accurate because they all produce images that look like the black hole that we observe. But sort of the remaining uncertainties about things like the magnetic field strength, things like the spin of the black hole, those are things that we couldn't start to address because all the different choices made similar final images at the resolution that we were observing at. Fortunately, we're able to use more information than what we obtained in the first images in the form of linear polarization. And this is the result that I've worked most closely on over the last few years, and so I've mentioned it. But basically, the first initial image that we released only has a fourth of the information that we actually observed. We observe the total intensity of light, but we also observe the degree to which light is linearly and circularly polarized. So the direction of light on the sky, which is now represented in our polarization results by these tick marks. These tick marks show the direction of the linear polarization of light across the image, which is the same image here, but in grayscale in the background. And so by comparing these results of polarization to simulations, it actually turns out that we can recover a lot more information about what the astrophysics of the source is. And you can see that just immediately by looking at this set of images from simulations in polarization, where they look quite different with different choices. So different simulation images show different structures that are strongly and weakly polarized. They have patterns that are radial or helical, radial here, like helical here. Just by looking at these images from simulations, you can immediately tell that polarization is really the key to learning about astrophysics from black hole images. And physically, this is because the synchrotron radiation that we observe from black holes is emitted with its polarization perpendicular to magnetic field lines. And so we immediately know that the polarization is going to contain some information on magnetic fields, which is one of the big uncertainties we have about what's going on around the black holes. And as the polarized light propagates through space-time, it's also sensitive to the magnetic field, plasma, and space-time curvature along its line of sight. So it's experiencing a lot of the physics here that is different in the different simulations and therefore drives different images at the end of the day. And so by comparing the simulations in polarization with our actual image results from the Event Horizon Telescope, we were able to show in 2021 and again in 2023 with a data set including circular polarization that the image, the black hole in M87 is likely magnetically arrested, or basically it has very strong magnetic fields which pile up on the black hole and push back against the matter that's trying to fall in. This is very important for trying to understand how black holes launch these jets of light, these jets of matter to very large distances, because we think that strong magnetic fields can extract black hole spin energy much more efficiently than weak magnetic fields, using this Blanford-Dinac process that was first laid out in 1977 and is sort of thought to be what powers jets throughout the universe by taking energy out of the spin of black holes. But that's never been conclusively proven. Okay, that's just a brief highlight of how we made the first black hole images and some of the many, many things we've learned about black holes from these images. Again, I skipped over a ton of things, especially in the second section, so please ask me if you have questions. But I just wanted to end the talk by talking a little bit about what we will see next, and how we're advancing in the HD collaboration, both on the sort of side of advances to our telescope array and in terms of advances to the imaging software and methods that we use to take our data and produce. So the first open area that we're addressing, hope to address in the next 2 years, is black hole dynamics. So again, as I mentioned earlier, black holes are highly dynamic, and Sagittarius star in particular in our galactic center is varying on minute-to-minute timescales, which makes the imaging challenge, taking a picture of it very difficult. Sagittarius star also flares very brightly almost more than once a day. And trying to understand this variability in black hole flaring is one of the sort of key open questions in understanding the physics near the event horizon, especially that drives these jets and outflows. So tracking motion around the event horizon, if we can do that dynamically instead of just being a static image, will allow for new tests of plasma physics, accretion, and gravity in this regime. But it's incredibly difficult because, again, as I said earlier, we're basically trying to take a picture of something that's moving underneath our camera aperture as we take an exposure. And so we need a combination of both more telescopes to get more data to make this a less opposed problem, and more innovative data reconstruction methods. This is just summarizing that same what I just said. Basically, each frame of a video only gives us a few different data points a few different data points, and each of these sets of data on their own is not enough to constrain the image if we try to do the inverse problem. Basically, if we try to recover frames of a video independently, we get junk and noise. But we can try to combine information across different video frames in order to stitch these data sets together and solve for a movie. This is essentially this temporal regularization, which was introduced first by Katie Bowman and Michael Johnson to try to use data to force frames in a video to be similar to each other as a new form of regularizer, to sort of use data across the whole series of observations in order to produce a movie. Now, we applied this in our first images of Sagittarius star in 2022. Unfortunately, we found that it was, even with our most sophisticated image reconstruction algorithms, quite difficult, given the limited amount of data we had in our first set of observations, to say anything conclusive about how Sagittarius star is varying. And so we looked at, for example, these two movies, which are exploring the range of temporal regularization, this sort of how connected different frames in the movie need to be. And you can see that they give different answers. Basically, if we have a lower temporal regularization value, we see this sort of flip in the brightness of Sagittarius star as it evolves. If we have a higher temporal regularization value, basically the movie is static. And despite our best efforts, by doing all the sort of tests and cross comparisons and checks that we like to do in the HD to make sure we're saying things that are robust and are consistent to various different choices in the imaging process, we weren't able to distinguish between these two in the end. Basically, there was nothing that allowed us to say this movie was better than this movie. And so in this initial data set, basically, even with our most sophisticated methods, we were just hitting the bounds of what we can do with how limited our data is. But in future years of observation and future data sets, I think we have a lot more data, and we've advanced our methods even further since then. And so I encourage you to stay tuned. I think we have more information on the dynamics of Sagittarius star that we should be able to see in the next few years. Okay. The The next set of advances that we hope to make is imaging in high dynamic range. So this is basically the fact that we think we see in around these black holes emission at orders of different orders of magnitude of brightness. We have this very bright emission around this supermassive black hole here in linear scale. We also have this large set of extended emission at very low brightness, hundreds of times dimmer, that tracks the outflow or jet emerging from the black hole. And we'd really like to be able to image not just the stuff very close to the event horizon, but to try to capture a full picture of what is nearby and then also farther out. But with our limited number of data, the EHT in 2017, we were not able to do that. Basically, we can recover a good image of the structure close to the horizon, but the structure that's 100 times dimmer and further out is essentially unconstrained by our imaging methods. This is something we're rectifying now or have been over the last few years by sort of adding new telescopes to our array. Basically, by filling in this plane of measurements of complex frequencies, we are able to start to look to get more confidence in our image reconstructions and probe dimmer and dimmer features in the image. And this is particularly powerful because the number of observations that we can obtain goes as the number of sites squared. So every site we add gives us much more information. And so we started with observations of 6 sites in 2017. As of the last few years, we're now observing with 9 sites, and hopefully, as we go into the next decade, we'll expand. There are multiple different proposals to expand to more than 15 sites. So hopefully, by adding all these new telescopes and combining and building an even larger global collaboration, we'll be able to probe in really fine detail sort of large-scale structure as a connection to the structure around the event horizon. And this is just an example of what this would look like for one particular proposal, the NGHD proposal, how adding new sites to the array will allow us to go from this reconstruction where we are only starting to, where we can't constrain anything about the high dynamic range features, this reconstruction where we can look in detail at what's going on in the low brightness region. And there's many different interesting physics cases that we can do, trying to illuminate with this type of image, trying to illuminate the black hole jet connection, trying to understand what the inner shadow or the emission interior to the ring is doing and how that connects with ground relativity. Our last future direction on the image side is high resolution. So you can see that our images are very blurry, but we think that underneath our blurry images, which are again only just beginning to resolve the black hole, that there's a lot of structure that's very informative of what's going on in space-time. In particular, we think we're seeing things that we think in our image underneath the blur, there should be signatures of photons that wrap multiple times around the black hole. And you can see in this animation or in this visualization that photons that wrap multiple times around the black hole that are pulled by the strong gravity of the black hole actually end up on the image plane in these very narrow ring features, these so-called photon rings. So if we can start to resolve this very narrow structure, we can start to understand how black holes lens light in sort of the most extreme regime that's ever been probed. And this is a simulation showing that, again, we have this sort of diffuse emission in the front, which is the direct rays, the blue rays here, coming directly from the image, directly from the plasma surrounding the black hole, still experiencing a lot of deflection. And then we have this very narrow photon ring that's bent around the black hole, that's caused by photons bent around the black hole multiple times. And with DHT, sorry, it's slow. Yeah, with DHT, we're blurred out and we can't distinguish these features. What we hope to do in the future is to extend the resolution of our telescope by putting a observatory in space that can connect all our observatories on the ground by going beyond the bounds of what Earth allows us in terms of the size of our telescope in order to produce the highest resolution possible and the highest resolution ever achieved in astronomy. And so we're targeting this with a NASA Small Explorers proposal in a mission called BEX. There are also various other concepts out there in the EHT collaboration and beyond in terms of how we can do this space VLBI. But basically the idea is that by adding a space orbiter to our EHT array, we would be able to we'd be able to extend the resolution by over a factor of 3 um, and probe the extreme lensing of this photon ring, but then also start to reveal the shadows on sort of the EHT scale of dozens of sources beyond what we've already observed. And so for just the gravity case of what the photon ring would look like with Bex, this is an example produced by my colleague Paul Tita, who has used a very sophisticated new imaging code called Comrade to produce it. Basically, this is what we would have hoped to observe in sort of the next decade with Bex if we were able to get a space-based orbiter extension EHT array. Okay, that's what we're hoping to do on sort of the array side, and by adding to our physical EHT. In the last 5 minutes, I'll just mention a few highlights of how we're pushing imaging forward on the computational side using different and new algorithms. So again, I think we sort of took the first steps now more than 5 years ago by doing this direct forward modeling imaging. Now I think that seems very primitive and basic compared to what different teams are doing nowadays. And it's really this connection and competition and collaboration between all the different groups of EHT that's pushing us forward, both on the hardware side and on building and applying different methods to extract the most possible out of our data. I think it's, again, the comparison across methods and different techniques that has really allowed us to focus in on what the most robust features in the images are, but by developing new techniques which all make different assumptions, we're able to extend that exploration further and we can get even higher quality images. So this is a very biased sample, only a few, like many different approaches people are taking. I'm showing a few highlights from across the EHT collaboration. So one is one work that I've already been doing, which is using multi-frequency data sets. Basically, by tying together information that we observe at multiple different radio frequencies, we're able to obtain higher quality images. And we're also able to map the spectral index or the evolution of the image across different frequencies in order to probe the plasma physics of black holes. Another I've already mentioned is a set of sort of truly Bayesian imaging that is now being done regularly by codes like FEMIST, DNC, and Comrade. These are new methods that use modern sampling techniques and GPU acceleration to sort of measure posteriors for each individual pixel in sort of hundreds by hundreds of pixel arrays, and sort of fully explore the uncertainty of what the image of what our images are in a much more rigorous statistical sense. And they're able to jointly solve for the image instrument gain terms and prior hyperparameters using GPU acceleration. Another example is to sort of move beyond the sort of very flexible general purpose imaging that has been done in the first EHT papers and try to impose more physical structure about what we think black hole images should look like. And one way that's been done is to use principal component analysis in this code called Primo to learn an image basis from a large set of simulations and basically use the image basis of simulations to sort of even super resolve our image even further from beyond what we obtained in 2017. So this is essentially filling in our gaps in Fourier space in a more physically motivated manner, using information from simulations in order to produce a more physically motivated prior for what our image should look like. And we can go to sort of this image, and this is the result from Primo from my colleague Leah Medeiros. And you can see that by using this different basis of geometry simulations, we don't produce these not-like artifacts that are common in sort of the more general purpose imaging algorithms. And this also allows for direct comparison of results of simulations. Another advance that's being done by my colleagues Katie Bowman and Bertie Fung is to sort of learn new image priors in a flexible way using diffusion models. So this is a new method that basically builds image priors trained on different sets of natural images from different domains, so sort of natural images, simulation images, simple analytic model images, in some cases even images of human faces. Those don't work very well, I think, but you basically train a diffusion model on a different image set and apply it as a prior in this framework, and essentially estimate a posterior distribution on the images using variational inference. And this is sort of what they obtain with this flexible method, looking at different image sets as their different priors. And so you can see when they use sort of generic natural images as priors, they obtain something that's very similar to what we obtained if you don't blur it to the original official image. But if you use detailed simulations, sort of analogous to what Primo was doing with principal component analysis, you could get a very crisp image of the black hole using your simulation priors. If you use more simple analytic models, you get something slightly different. And then if you use people's faces, you still get a ring, but there's a lot of extra structure. There are similar sort of machine learning-based techniques that are now being used regularly to sort of track image dynamics. So I think a really exciting result that's come out of the group of my collaborator Jose Gomez and his student Mariana Fashi is this code called Kine, which basically uses implicit regularization of a neural network in order to um, um, to regularize the image both in time and space. So this is an example of what's obtained from this particular method by, in terms of these real observations of this black hole jet. And you can see that Kine is producing this very beautiful, smooth image of this jet, whereas traditional image reconstruction with clean produces something much more choppy and lower resolution. And I think understanding the detailed structures of these jets is very important for understanding exactly how black holes feed back on large scales. And so we can get this higher level of detail from these new imaging methods, that'll be really exciting. And lastly, I just want to mention a project that I've been involved in, led by my colleague Aviad Levis, who is at University of Toronto. And this is basically trying to take the next step forward and not just image 2D structure on the image plane, but actually try to image the 3D distribution of plasma around the black hole by using this technique called BH-NeRF, which is using a neural network called NeRF, initially developed to sort of synthesize different views of physical space taken with different cameras at different angles, and using the fact that we have, in a black hole case, we actually are observing emission at different angles because we have strong gravitational lenses. Because stuff is moving, because light is being bent around the black hole, and each individual light ray is actually seeing different views of the source distribution. We can sort of try to apply both using physically motivated ray tracing and the implicit regularization of a neural network to model the smooth distribution of matter around the black hole. We can actually try to obtain from EHT observations, or in this case, propose future EHT observations, which are usually have a lot more information. We can actually start to obtain good reconstructions of what sort of the distribution of material is, of matter is, as it swirls around the black hole in 3D space. Okay. So again, that's just a highlight of a few methods that we're exploring these days. There's many more that people are developing. I think it's really been exciting to see as we opened this sort of new field of black hole imaging, how people have taken our very simple approaches from now more than 5 years ago and expanded it into a huge new literature of ways to do black hole imaging. And again, I think we learned the most from comparing these results to each other and testing them rigorously against each other and focusing on what the most robust information is. And so, yeah, this is the final summary slide. The future black hole image of astrophysics, I think, is incredibly bright, both by expanding our ground-based EHT array, by going to space, hopefully, and by developing new algorithms and new inference techniques. I think all these three pillars together will allow us to say to probe a lot of interesting new black hole science on multiple scales. I'm really excited to see where the field goes next. So yeah, here's just my summary slide. Here in a second. And yeah, thank you again for having me and for the award, and happy to answer any questions.
Thank you for a wonderful talk. I major in mathematics, and you mentioned in your talk many times simulated image. So I'm very curious how you simulate a black hole.
Yeah. Go back.
That's numerically solving some differential equation.
Yes, exactly. So this is a whole other field that I summarized in one slide. But basically, we have a particular model for the fluid around the black hole, which we model by magnetohydrodynamics. This is itself a huge assumption, potentially. And we evolve that magnetohydrodynamics coupled to general relativity and the general statistics curve space background of the black hole. And we then sort of apply different initial conditions and see how different choices for the plasma distribution create different structures around the black hole. And similarly to what I was saying about imaging methods, I think there's also a lot that we've learned from EHT by comparing different codes, by comparing different methods for doing the simulation about what the most robust and interesting features of plasma around black holes is. But basically, we have these 3D supercomputer simulations, and then we do ray tracing through them to produce actual images. We essentially say, if we have a distribution of matter, which we've obtained from solving a differential equation, what does the actual image look like at the end of the day if we can model the emission of that matter, synchrotron radiation? So this is capturing both the dynamics of the plasma, background space-time, both in how it affects the plasma and how it affects the light. It's a very complicated nonlinear image. Oh yeah, that's a really good question actually. Yeah, so better image of that. Um, yeah, so we think, or I think we know that the reason that this ring is asymmetrical is because we're viewing it at an angle. So essentially, matter is orbiting around the black hole, and it's orbiting at speeds nearly the speed of light. And as matter moves toward us at nearly the speed of light, the light is Doppler boosted toward us. Essentially, its intensity is enhanced by Doppler boosting, and as matter recedes away from us, its intensity is diminished. So essentially, the matter is orbiting this way around the black hole. Um, we're not viewing it because we're viewing it not face on. We see that sort of difference between the top and bottom. Yeah, exactly. So we can actually use this to determine which direction the black hole is spinning, because we think well, we have tested with simulations that in all the simulations, the matter at this radius close to the black hole is spinning with the black hole. The black hole drags the matter with it in this frame dragging effect. And yeah, because we see the asymmetry on one side, not the other, we can then tell that the black hole is spinning with its angular momentum into the sky, essentially.
Thank you for the talk. You covered all my questions, like 3D, in space, whatever. But I was wondering how much uh, acquisition time is required from the telescopes. How is this coordinated? Because I can imagine that each telescope has its own
Yeah.
schedule, and you guys want it all at the same time.
No, that's a really, really good question. So, for these initial images, we basically had 4 full days of observation where each telescope basically observed for 24 hours, large fraction, as much of the 24 hours they could actually see the source for 4 full days. But yeah, we faced a really challenging problem because all these telescopes that we use were built for other things, right? None of them are directly built to just do ESG observations. So they have other commitments. They have different people running them. They have different schedules. Sometimes they break. So actually, yeah, challenging these observations and determining um, how much time we need on each of them is itself a really interesting logistical challenge, and one that people have invested a lot of time in. Yeah, as we get more and more telescopes, I think it becomes less and less critical, because we have a denser array, we can start to lose one telescope at different times and not lose our complete ability to make an image. But yeah, ideally we want all of them. So yeah, coordinating the scheduling is a huge heroic work that is above my pay grade, but it's really important.
And on that regard, is there a time of the year that
Yeah.
is better to do this, or is it all the same?
No, absolutely, it is not the same. And back to the array picture. So basically, we can only observe at certain times of the year, and we observe in the early spring typically, because the sources are only visible from all of the sites at that time. As the Earth moves around the sun, the sources rise and set at different times, and for more northern sources, we can only see them for different parts. For more northern sources, the southern telescopes can only see them at certain times of the year, and vice versa. And so early spring is sort of the sweet spot. It's also the sweet spot in terms of weather. So all these telescopes have to be at very high altitudes in order to um, observe robustly. And so we want some time that isn't summer for either of them, because the summer weather, um, either the northern or southern hemisphere, because the summer weather produces more water vapor in the atmosphere, which makes our imaging problem even more challenging. So yeah, we typically observe in spring. Hopefully we're able to extend that into larger time baselines. A project we have proposed for is to actually observe M87 over the course of like 3 to 4 months next year. We'll see if that proposal is approved. But typically, we've always observed so far in April.
And the one in space, where would it be?
So the one in space that we proposed would be, or hoping to propose, would be in sort of a mid-Earth orbit, so sort of halfway to geosynchronous orbit. The further out you get, the higher resolution you obtain, but then it becomes more challenging to transmit the data to the ground. And so that's sort of the sweet spot we've arrived at now. Like I said, there's multiple proposals. This isn't the only. This is just one that I'm involved in, but there are other proposals in space OPI of different configurations.
Okay, due to the time, this talk is stopped here, and let's give thanks to the speaker again.